Hello everyone. Welcome to the next lecture on the real analysis. Today I will explain you how you can solve the problems related to the uniform convergence. Myself Dr. Harish Garg. You can follow my YouTube channel where you can find the playlist of the real analysis. In this playlist you can see I have already covered the various lecture related to the sequences of the functions and their subsequent CSR-net problems with the help of the shortcut tricks. Now I started the series of the function problems. Once I cover the theory lecture complete, and then I will explain you again the CSR-net examination problem. You can subscribe my YouTube channel so that when I upload my next video, you will get the notification. Now, what we have discussed in our last lecture, we have covered the topic of the uniform convergence of the series of the function. In this lecture, we will cover about the examples of the uniform convergence. Always remember, whenever there is a question related to check the uniform convergence of the series, examine the uniform convergence of the series, prove that the uniform convergence of the series, and so on, your first target come in your mind to check the pointwise convergence and the uniform convergence. Make sure, student, if the series is not pointwise convergent, fine, then this implies it is not uniform convergent. And how you can check about the pointwise convergent, that I already explained in my previous lecture. That's why I'm asking you to follow my YouTube channel and subscribe it so that you will get the notifications and deep understanding. Now, once you have the series of the function, your first target is to define the sequence of the function, which is called as nth partial sum sequence, which is defined mathematically as u1x plus u2x and unx. This Fn is called as sequences of the function. Remember, student, it's a sequence of function. Based on this sequence of the function, we can define the pointwise and uniform convergence. I will explain you the two different methods for finding the or you checking the uniform convergence. One is based on the standard definitions. Second is the WM test. In this lecture, I will explain you with the help of the definitions. Now, what are the various steps I can follow? I will define the three-step rule. In the first step, I can define the value of the Fnx, that is the nth partial sum sequence. Second step, I will check once you know the Fnx, we can define the pointwise convergent. What is the meaning of the pointwise convergent? We can take the limits as n approaches infinity. If this limit is my existence and unique, then we can say the series or the sequence of the function converges pointwise. And once we know the pointwise convergent, the third step is we will check about the uniform convergence. Or we can also use the Mn test, which is defined as supremum over the domain such that Fnx minus Fx. We will find these limits. If it goes to 0 as n approaches infinity, then our series is my uniform convergent. For more detail about these two lectures, I recommended you must watch about these lectures. I will follow the same way as I explain in my this lecture, which is available in this playlist. Example of the Mn test and the examples of the uniform convergence of the sequence of the functions. So let's start with the examples. Remember, the first example is you have to show that the series is uniform convergent on closed interval a comma infinity where a is strictly greater than 0. Fine. How you can prove that? Firstly, because it's a series, the first expression is my u1, second is my u2, third is my u3. So can you write the expression of the u and x? Can you find the nth term? It is x. It is the second term, start from the 1 and 2. Third term, start from the second and third. I can write this expression. Then always write in the partial fraction. Fine. How you can write the partial fraction? Let's say I can write this simple example for you. How you can write this into the partial fraction? You can write the denominator into the separate form. Fine. Now substitute this value as a 0. The value of the x will be minus 1. You can substitute x is equal to minus 1 on the left hand side apart from this x plus 1 quantity. So it will be minus 1 plus 3 divided by minus 1 plus 2. The answer is 2. Similarly, for this case, the x will be my minus of 2. I can substitute everywhere apart from this quantity. So it is minus of 2 plus 3 minus of 2 plus 1. Answer is minus 1. This is the way you can partial fraction. Similarly, in this case, you can write the partial fraction. For this one, I can substitute x is equal to minus 1 over n. I can substitute everywhere apart from this term. It is minus 1 over n. It is minus 1 over n. So it is minus 1 over n, and its n will be cancelled out. It's a plus 1 over n. Answer is minus 1. Similarly, if you do this calculation, it will give you the plus 1. Fine. So your partial fraction is this term. Then we can define the step number 1, nth term. I can substitute the value of the u1. I can substitute n is equal to 1. It is 1 minus 1 plus x. N is equal to 2. 1 plus x minus 1 plus 2x, and so on. Now clearly say the second term will be cancelled with the first term. This value will be cancelled out. Third term will be cancelled out. And the only term which is left behind is the first term and the last term. If you take the LCM, it is nx over 1 plus nx. Once you know the value of the fx, then our target is to find the pointwise convergent. The domain is a comma infinity. So I can find this limit corresponding to the two cases when x is equal to a and when x is not equal to a, or you can say x is greater than a. What is the value of the fn? What is the value of the fn when x is equal to a? This is na over 1 plus na. Then take the limit as n approaches infinity. It is my infinity over infinity form. I can apply the L'Hopital rule. It's a over a. This is my 1. Similarly, when x is greater than a, I can take this limit as n approaches infinity. So clearly say this is my infinity over infinity form. I can apply the L'Hopital rule. It's a x over x. Again, this is 1. And clearly say the limits are existence. This implies the sequence of the function fn converges to the f pointwise on this interval a comma infinity, and hence the series is also converges pointwise. Now the next way is your target is to find the uniform convergent. So before I explain the uniform convergence, I hope you can like and comment on this video. You can support my efforts by putting the like and in the comment box. Now I can say this is always 1 for all x. Now my expression is fn minus f. What is the value of the fn? It is nx over 1 plus nx. What is the value of the f? Is my 1. So if you take the LCM, you will get the 1 plus nx. Fine. Or you can also use the MN test. Or you can use the MN test as well. Fine. But the first two example I will solve with this example this way. Third, fourth onward examples I will explain you with this method. I can substitute this value at the given point and you will get this value. Your target is to find the value of the n. So I can take the reciprocal. It is 1 over epsilon. The value of the n is 1 over x, 1 over epsilon minus 1. Once you reach at this point, your target is always consider the two cases. The first case is, can you choose the value of the x so that n will be my infinity? The first case. Second is, your target always to find the maximum value of this expression. Fine. Now if I consider this case, can you choose the value of the x so that n becomes the infinity? Only case is when you approach x approaches 0, because it's an open interval. So whenever x is very, very small, this expression will goes to the infinity. And once n is my greater than infinity, you are unable to find a positive integer m, so that this condition hold. That means fnx does not converges to the f uniformly near to the point x is equal to 0. That means the series is not converges to the f uniformly near to the point 0. Or you can say the series un is not uniform convergent on any interval which contains the point 0. That means What is the meaning of that? That means if you consider the interval minus 3 comma 7, it is not uniform convergent. 0 comma infinity, it is not uniform convergent. Open interval minus 2 comma 7, again it's not a uniform convergent because 0 lies that. That's why in the given statement, if you closely look about that, it is strictly a greater than 0. Now the second case here, your target is to find the maximum value. How you can find the maximum value of this? Your target is to find the maximum value of this number. Clearly say this number is my constant. So your target is to find the maximum value of 1 over x, which is equivalent to the minimum value of the x. Now what is the minimum value of x? Is a. So your maximum value is 1 over a epsilon minus 1. Once you know this number, therefore I can choose a positive number am, which must be greater than of this maximum number. And because this is my maximum value of 1 over x epsilon minus 1 for all x in the domain. Therefore, we are able to choose the value of the m. Hence, the series is uniform convergent on the closed interval a comma infinity, where a is my strictly greater than 0. Remember student, in this particular example, we have seen the series is pointwise convergent on the a comma infinity, where a may be 0 or a is greater than 0. But the series is converges uniformly on the a comma infinity, provided a is strictly greater than 0. Fine. Now look at the second example. Again, you are talking about the series. This is my un. Your target is to write the partial fraction again. So I can write this quantity is 1 plus x over n, and this is 1 plus x over n minus 1. So if you do the partial fraction, you will get this expressions. I can define the value of the fn, substitute the value of the u1, clearly say this number will be cancelled, second term will be cancelled, and this expression cancel out. Sorry, this expression will be there and this last term will be cancelled out, and your expression is this term. Now, what is your target? Show that 0 is the point of non-uniform convergent. That means whenever x approaches 0, your target is to prove n approaches infinity. This is your target. Fine. So again, very simple. Firstly, I will check about the pointwise, because as I told you, if it is not pointwise, this implies it is not uniform convergent. What is the domain in this case? Domain is my real line R. So I can consider three cases: x is greater than 0, less than 0, and is equal to 0. Now, firstly, I will choose about x is equal to 0. What is the value of the fn x when x is equal to 0? 2 over 1 plus 1 minus 1, which is 0. So the limit is also 0. When x is my positive, then 1 plus x is my greater than 1. What will happen if you consider raised to power n? It goes to the infinity as n approaches infinity. So the limit, this expression becomes 2 over infinity minus 1. That is my minus 1. Similarly, when x is my less than 0, 1 plus x will be less than 1. This implies 1 plus x raised to power n will goes to the 0 as n approaches infinity. So I can substitute this. It's a 1 plus 0 minus 1. The answer is plus 1. And you can see in all the cases the limits are existence. Therefore, the series is my pointwise convergent. Now for the uniform convergent, again your target is to find the value of the n. We have the three different cases. I can substitute these three cases here. When x is 0, this is my fn x. Fx is my minus of 1. If you subtract them, your answer will be 2 over 1 plus x. When x is equal to 0, what is the value of the fn is? 0. Fx is also 0. Answer is 0. And this minus of this, and your expression is this number. Now, since my target is to prove only for the non-uniform convergence, because whenever x is 0, 0 less than epsilon satisfied, either you can consider the third case or you can consider the first case. So let's start with the first case. I can substitute this value fnx minus fx in this given expression, and your target is to find the value of n. I can take the reciprocal, it is my epsilon, sorry, 1 over epsilon, and 2 I can multiply them. Fine, I can find the value of the n. This number is greater than 2 over epsilon minus 1. I can take on the logarithm on the both side. So it's a log of 2 over epsilon minus 1 divided by log of 1 plus x. Now, can you choose the value of the x? Can you choose the value of the x from the given domain so that n becomes my infinity? Fine. So clearly say when you take x is 0, log 1 is 0, it will goes to the infinity. And that point is called as my non-uniform point of convergence. And that's the same thing they are asking about this statement. Fine. In this problem, they are not asking you to check the uniform convergence of the series. They are asking you to prove the uniform point of non-uniform convergence. That means whenever n will be infinity, you are unable to find the value of n. Hence, the series is not uniform convergent. Or you can say the series is not uniform convergent and 0 is the point of non-uniform convergence. Look at the third example. Discuss the uniform convergence on the closed interval 0, 1. This is the expression of the un. It is already a partial fraction. So my target is to find the value of the fn directly. What is the u1? I can substitute the value of the n is equal to 1. Is x over 1 plus x square, 2x over 1 plus 4x square. This is my u1 plus u2 and so on. The first term will be cancelled, second term will be cancelled, and the last term will be remaining. The first and the last term pending. Based on this expression, my domain is the closed interval 0, 1. So then I will compute these limits and check whether this limit is existence or not. If the limit is not existence, then it is not pointwise convergent, hence it is not uniform convergent. What will happen if x is equal to 0? What is the value of the fn? 0, 0. So then the limit is also 0. What is the value of the fn if x is equal to 1? 1 over 2 n plus 1 over 1 plus n square. Now if you take the limit as n approaches infinity, this is half. This is my infinity by infinity form. I can apply the L'Hopital rule. It's a 1 over twice n plus 1. Clearly say this will goes to 0 as n approaches infinity. Whenever x lies between 0 and 1, I can simply take the limit as n approaches infinity. This part is my constant with respect to n. Again, it's my infinity by infinity form. I can apply the L'Hopital rule. X twice of n plus 1 of x square. Clearly say again this part will goes to 0. So my limit is x over 1 plus x square. Clearly say half is a particular case of this when x is equal to 1. So either you can combine the two cases when x is 0 and x is this way. Fine, you can combine them in this manner also. Now, because the limits is existence, so therefore series is also pointwise convergent. Now, for the uniform convergent, you can apply either of the way. So for that, I can firstly find fn minus f. This is my fnx. Fx is my this case. If you subtract them, this value will be cancelled. The only expression left behind is this one. Fine, and you will get this. Now either you can use either one of them, but I can prefer to this way. Fine, whenever there is a denominator part, always prefer the supremum part. Fine, or you may use this one, there is no issue about this case. Now again there are the two methods. The first method is you can consider this expression is my y. Fine, find the maximum value of the y. How you can find the maximum value? First derivative 0, second derivative less than 0. Or second method that is quite easy and interesting. In this particular example, my domain is 0, 1. You can choose any of the subsequence in between them. It may be 1 over n, it may be 1 minus 1 over n, it may be 1 over n plus 1, or it may be anything. Fine. You can choose this method only if you choose any of the subsequence, substitute value in the given m, and if it not goes to the 0. If it not goes to the 0 as n approaches infinity, then you can say this is my not uniform convergent. So that this second method is applicable only if you want to prove that this is not uniform convergent. And if you substitute x is equal to something in the given expression, and if it goes to the 0, then you have to apply this method. Fine. So this method is very useful once you are in the competition exam, like CSR net, GATE, or any other case. So I will explain you this because it's n plus 1. I can choose this. What is the value of the mn? It is my 1 plus 1, which is half, which is not goes to the 0. Therefore, by the mn test, the series is not uniform convergent. Fine. Moreover, you can also see the value of the x is, it goes to the 0 as n approaches infinity. Again, this point 0 is called as the non-uniform point of convergent. Look at this next example. You may use as the second method also, like y is equal to something. Fine. That I will explain you with the help of this example. This is my u1, this is my u2, this is my u3, and so on. Can you write the un? It's a very simple. You can see it's a 2 square, it's a 3 square, then it's a n square. Divided by 1, it's a 2 cube, n cube, x square, minus. It's a x, it's a 2 square, I can written as a 1 square, it's a n minus 1 square of x. And the below one is n minus 1 cube x square. Fine. This is the expression of the un. Since it is already a partial fraction, I can start with the fn. I can substitute the value of the u1, u2, and u cancel. Clearly say the first expression cancel, this value will be cancelled, n minus 1 will be cancelled. The only term which is left behind is n square. Domain is my 0, 1. So I can start the pointwise convergent. Again, I can case the x is 0, x is 1, x lies between 0 and 1. What will happen if x is equal to 0? Answer is 0. If x is equal to 1, your result will be n square over 1 plus n cube. And if you take the limit as n approaches infinity, it's a infinity by infinity form, then 2n over 3n square. So clearly say it goes to the 0. Whenever x lies between 0 and 1, we can take this limit. Again, it is my infinity by infinity form. I can apply the L'Hopital rule. So 2nx, 3n square x square. 1x cancel, 1n cancel. Again, it goes to the 0. So I can say this term is 0 for all x belongs to the 0, 1. Fine. So since the limit is existence, therefore the series is uniform. Series is pointwise convergent. Dear student, I hope you can like and comment on this video as well. Can you find the value of the fn minus f? Fn is my this, fx is my 0, so expression is my same. I can substitute this value in this expression. Your mn is my this. Again, you have the two different methods. You can choose y is equal to n square x over 1 plus n cube x square. Find the value of the y dash to be the 0, y double dash less than 0. Or because my domain is 0, 1, I can choose any of the subsequence from this one. So let's say 1 over n. Again, remember student, I told you this method is applicable only when mn is not goes to the 0. Fine. If mn goes to the 0, then you can't apply this method. So what is the value of the mn? It is my n over 1 plus n. Then what is the limit as n approaches infinity? 1, which is non-zero. Therefore, you can use this method. You can say the series is not uniform convergent over the closed interval 0, 1. And again, you can see I can say this is a 0. So 0 is the point of non-uniform convergent. Second method, you can solve this way in the examination as well. There is no issue. But if you want to solve like this manner, I can find the y dash. Remember, the derivative with respect to the x. So what is the derivative? It's a n cube x square. So I can use the quotient rule. Derivative with respect to x is n square minus, it is my 2n cube x. Now if you open this bracket, it's n5 x square, you will get this term. Now y dash is 0. For the maximum minima, y dash to be 0. So the value of the x is plus minus 1 over n raised to power 3 by 2. But my domain is the positive interval, so I can consider only as the positive value. Then my target is to find the y double dash to be less than 0. But you can see it's very difficult to find the second derivative. Fine. Then the other way, the easiest way is I can use the first derivative test. How you can apply the first derivative test? That's a very simple. I can consider this value 1 over n raised to power 3 by 2, and we will look about the sign of the y dash. How you can find the derivative sign? It's a very simple. I will tell you. Look at that. This number is my positive. So 0 is lies somewhere here. Fine. If x is equal to 0, what is the value of this? X is 0. This number is my positive. Fine. And if x is some another value which is greater than of something, then this expression is my negative. So this part is my negative. This is a sign of the y dash. Now once it changes the sign from the positive to negative, that means this point is the point of the maximum. On the other hand, if the point is changes the sign from the negative to the positive, then that point is called as the minimum point. My target is to find the supremum, so therefore my point is maximum point. I can substitute this value of the x in the value of the mn. You will see the answer is n square over n raised to power 3 by 2, 1 plus 1. It is my root of n divided by 2, which is not goes to the 0 as n approaches infinity. So that means you can say the series is not uniform convergent on the closed interval 0, 1. Fine. Moreover, you can also see the quantity which you have obtained is my 0. So therefore 0 is the point of non-uniform convergent. Or you can say the series is not uniform convergent on any interval which containing the point 0. And you can see in the given statement they are considered the point of 0 as well. On the other hand, this series is uniform convergent on this series, on this interval. This series is uniform convergent on a comma infinity, provided a must be greater than 0. Okay, look at one more example. Test the uniform convergence. Again, my series is un. It is already the partial fractions. I can substitute the value of the u1, u2. It is cancelled out. The only expression left behind is, what is the domain of this case? Domain is my real line R. Fine. So I can start with the pointwise convergent. I can consider the two cases. Either x is 0 or x is non-zero. What will happen if x is equal to 0? So it's a 0 over 1, 0. If x is non-zero, then it is my infinity by infinity form. Then by applying the L'Hopital rule, it's a 4n x square e raised to power n square x square into 2n x square. So again, as n approaches infinity, this term will be 0. That means fx is equal to 0, which is existence, hence is a pointwise convergent on the R. Again, I can apply the Mn test. I can start with the fn minus fx. I can substitute this value in the given expression. Again, my domain is a 0, 1. I can choose any value of the x. Say again, x is 1 over n. So what is the value of the mn? It's a 2 over e, which is not goes to the 0 as n approaches infinity. That means the series un is not uniform convergent on R. Or you can say the series is not uniform convergent on any interval which contains the point 0, because the domain is my R and 0 belongs to the R. This is the first method. Second is you can consider this expression as a y. Find the y dash. Fine. Then y dash is 0. This implies x is my 0. X is my plus minus 1 over n. Now the domain is the plus r. It consists of the plus 1 by n minus 1 by n both. So now we will see the sign, because again it's not an easy target. You can find the y double dash. So how you can find the maxima and minima? I will look about the sign of the y dash. Again 0 lies on here. When x is 0, this number is, when x approaches 0, this number is my positive, this number is my positive, the whole expression is positive. And this part is my negative, because whenever x is a larger number, this number is my negative. Similarly, in this case 0 lies positive and 0 is. So clearly say this point is my point of the maxima. This point changes the negative to the positive. This is the point of the minima. But we need a supremum. That's why we consider the 1 over n only. Once you can substitute the x is equal to 1 by n, what is the value of the mn? It's a 2 over e, which is non-zero. Hence, the series un is not uniform convergent on the given domain or on the any interval which contains the point 0. Fine. Or the any interval which contains the point 0. Now since x is equal to 1 by n is the point of the maxima, what is the limit as n approaches infinity? So 0 is the point of non-uniform convergent. Look at the another one. The uniform convergence is given. So un is given to be this case. Fine. So again, because the denominator is my 1, there is no need of the partial fraction. So I can start with the u1 directly. If you look about this term very deeply, this is my GP series. And what is the sum of the GP series? A 1 minus r raised to power n, 1 minus r. Clearly say A is my e raised to power x. What is the common ratio? E raised to power minus x. So I can substitute both the values. You will get this term. Or I can return this is my 1 over e raised to power x, and you will get this term. Now for the pointwise convergent, domain is my 0, 1. I consider the 3 cases. X is 0, x is 1, x lies between 0 and 1. So what is the value of the fn x when x is equal to 0? 0. So limit is also 0. What is the value of the fn x when x is equal to 1? 1 over e minus 1, 1 minus e raised to power minus n. And if you take the limit as n approaches infinity, this value will goes to the 0. The expression is 1 over e minus 1. And if you consider the limit as n approaches infinity, this value will goes to the 0. The expression is x over e raised to power x minus 1. Clearly say 1 over e minus 1 is a special case of this. So I can combine them. You can write in these two cases. Because the limit is existence, so it is a pointwise convergence on the closed interval 0, 1. Now to check about the uniform convergence, again it's on your choice whether you want to apply the MN test or you want to apply the by definition. Now clearly say in this case it is not written somewhere in the denominator, so I can apply to this definition. What is the value of the fn minus f? This is the value of the fnx. This is the value of the fx. If you subtract them, this expression will be cancelled out and your expression becomes this term. I can substitute the value in this case and try to find the value of the n. So it is a x e raised to power nx is less than epsilon times of this. I can divide it by x on the both side, taken the logarithms, and then we can get the value of n. Fine. Once you can find the value of n, we have the two cases. Can you find the value of the x so that n becomes my infinity? Clearly say, because of this expression, if I choose x approaches 0 and 0 is the part of the domain. So that means whenever x approaches 0, this quantity becomes my infinity. What does it mean? We are unable to find the positive integer m so that this condition satisfied. What does it means? That means fnx does not converges to the f uniformly on the interval 0 comma 1, or instead of the interval 0 comma 1 on the point where x is equal to 0. That means the series is not uniform convergence on any interval which containing the point 0. Therefore, the given series is not uniform convergent on the interval 0 comma 1. However, this series is uniform convergent on the semi-open interval 0 comma 1, because 0 is not the part of this. This series is also the uniform convergent on this provided a is greater than 0, and so on. Fine. So this is the way you can prove this series. For more detail about this uniform convergence, I recommended you can watch about the MN test of the sequences and the examples of the uniform convergence. These lectures are very useful for you, and along with them, you can watch about the pointwise convergence definitions examples. I hope you can like, subscribe and comment on this video. We will see the next lecture on the WM test. There's a second method for checking the uniform convergence. Till then, you can share this video with your friends and don't forget to subscribe my YouTube channel. Thanks for the watchings and thanks for the support. Happy learning, students. Best wishes.